the third of Purdue InMax July 2020 webinar series, Cost Optimization in Robotics and Co-Robotics Driven Production. My name is Mike Gerson, and I'll be introducing today's session as well as the presenters today. This webinar is hosted from Purdue's Intelligent Manufacturing Testbed facility in West Lafayette, Indiana, and was developed in collaboration with Purdue's College of Engineering, Purdue Polytechnic Institute, and the Wabash Heartland Innovation Network, or WIN, which is a regional initiative created through the generosity of the Lilly Foundation in cooperation with communities and businesses from all across Northwest Central Indiana. Before we get started, just a few words about InMac. InMac was created to strengthen Indiana's manufacturing ecosystem by enhancing the relationship between Industry 4.0 tool and skill set adoption and next generation workforce readiness. We do so through three core program areas: education and workforce development activities, invigorate talent pipelines in a highly accessible manner through a range of K-12 and incumbent workforce programs with our partners all across the state. We offer integration and innovation services in which we work with companies at their sites across Indiana to implement modernization projects. And more recently, we've added the Intelligent Manufacturing Testbed facility, which is a center that investigates ways for all manufacturers, regardless of their size, to overcome barriers to achieve Industry 4.0 in ways that work for them. Two more remarks about the testbed facility. We do conduct research in smart manufacturing and the digital twin across all levels of the manufacturing enterprise. The center provides a platform for industry to develop and validate technologies to integrate and manage data streams across the product lifecycle and entire value chain. The center includes a fantastic array of real-life production assets, including lightweight composites manufacture, injection molding, subtractive machining, subassembly, supported by rapid prototyping capabilities through integrated design and simulation suites, as well as some additive manufacture tools. Integrated into our manufacturing operations are also metrology equipment, in which we can provide rapid validation at the manufacturing cell, as well as offline. And through the manufacture of these real products, we leverage IoT technologies and real-time information streams to study and showcase ways to achieve Industry 4.0. As soon as the situation surrounding COVID eases, we look forward to seeing every one of you here in West Lafayette at an in-person seminar and workshop. We'll be providing information about our schedule as we're able to. All right. This webinar series, as I mentioned, is the third in the series for this month, and the content was developed by a diverse group of faculty that have been collaborating on a number of areas to launch this testbed facility. Today's session, in particular, is about cost optimization in robotics and co-robotics driven production. And through the session today, we'll provide a basic perspective of what technologies are available today in robotics and co-robotics, as well as we'll introduce some techniques to assess the economic impact for various production scenarios. Format: participants will remain muted throughout today. It'll be a 45-minute discussion, followed by a Q&A period at the end. Moderators will address questions as they come in through Zoom's Q&A tool. And at the conclusion of today's event, we request that you participate in our survey that will be distributed to you via email. Introducing our speakers today. First, we have Dr. Richard Voiles, who has a number of active testbed projects, including work in IoT integrated products, autonomous vehicle dispatch and control, as well as autonomous vehicles for industrial applications. Joining Dr. Voiles is Dr. Jonas Munson. Dr. Munson does some work with IoT sensors integration into products as well as production, as well as his work in technical cost modeling we'll be covering today. And Dr. David Capillari is also joining. His work in the testbed includes the introduction of cobots mounted on autonomous vehicles into production scenarios, as well as robot and effector and manipulations guided by heightened aware vision-based systems. We thank all of our faculty for preparing for today's session. And without any further delay, I'll pass it over to Dr. Richard Voiles.
All right. So thank you, Mike. And thanks to all of you for attending this third virtual manufacturing workshop for the Indiana Manufacturing Institute. Today we're going to talk about cost optimization for robotics. And your presenters for today are David Capillari, Ben Haley, Jan Anders Manson, and myself, Richard Voiles. And so what we want to, this cost optimization is we have a focus also on co-robotics. And we want to talk a little bit about how co-robotics differs and is similar to traditional robotics from a cost accounting standpoint. But first, let's talk about what we mean by a collaborative robot or a co-robot or what we started referring to as Robotics 2.0. And this era of collaborative robots, where robots are working symbiotically with humans, these are now in 2017 accounted for only about 4% of sales in 2017. But it was growing at about a 60% per year rate compared to 12% for conventional robots. And so by 2025, it's expected that co-robot sales are going to be about a third, or about 34% of all robot purchases are going to be in this new space of collaborative robotics. And that's why we think it's important to talk about both how do we cost traditional robots, but also how do we cost collaborative robots, and what are some of those challenges in integrating collaborative robots into manufacturing line. Now, when we're talking about that growth in sales that we're seeing, 60% per year growth in this segment of robotics, a lot of that growth is driven by small to medium-sized firms that are using these co-robots to get into more of a job shop environment, and that's kind of one of the goals. So again, the idea behind this Robotics 2.0, or as we have started referring to it, is that machines that work with humans as co-workers, and not just, and that's in the manufacturing vein. When we're talking about in the larger application of robotics to like search and rescue and everything, there's a number of things that deal with how these robots work, not just as fully autonomous and kind of lights out factories, but are in fully autonomous in a lights out factory, but how robots and humans use their respective strengths to do to achieve tasks together. Again, leveraging the strength of one another. And so when we're talking about co-robots, that they are intrinsically human safe. In other words, these are a special brand of robot that has some design features that make them, that limit the potential injury they can have to robots. To humans. They, again, as I mentioned, they're working symbiotically with humans as co-workers. And an important aspect of what this means is that they communicate with humans on human terms. And that's why we're seeing so much growth in small to medium-sized firms. It's, small to medium-sized firms rely a lot more on human workers to fill multiple roles. And so they need robots that aren't, that you don't necessarily put a lot of money into the initial installation and then maximize the incremental value. It's somewhat the opposite. A lot of times, we use humans to fill in gaps in an emergency. And that's the same way that these co-robots are increasingly being used. And that means they have to communicate more in a less trained environment, so that they aren't trained, that the human co-workers are not quite as much dedicated training for that specific job. And so again, this idea is to focus on task experts rather than programming experts. We want these robots to work with and learn from their human coworkers. And so again, we've been calling this Robotics 2.0. Let's also talk back, kind of look back at, well, what did we mean by Robotics 1.0? And I mentioned the lights out factories, and that really was the goal for the first few decades in robotic development and deployment, was this idea that, yep, there are certain dull, dirty, dangerous tasks that equivalently dull, dirty, and dangerous robots could do in a manufacturing environment with no humans at all, right? The idea of full automation. And that was this idea of the lights out factory, and that humans only need, and the idea behind the lights out factory was humans only needed to be in there really to go and fix or repair the robots. And so, here's this classic example of a robotics 1.0 application, final assembly in the automotive assembly line. And in fact, fences were what defined this separation in robotics 1.0, because we had to keep the humans separate from the robots. Because again, they were not only dull, dirty, dangerous jobs, but they were dull, dirty, dangerous robots, because they didn't understand humans and how humans were, performed in the work environment. So we built the work cell around the robot as if no humans were in there. And so these fences we see in this environment, humans are excluded from where the robots are by these walls. And that's kind of the human zone. And then this red zone in the middle, the danger zone, if you will, is, where the robots inhabited, and the humans were kept separate, inhabited the green zone. The problem with this, with robotics 1.0, is it was really very successful for only a few niche industries. And the vast majority of manufacturing in the United States and in the world in general really can't be done well, or at least hasn't been so dominated by this version of robotics 1.0, the lights out factory approach. Because it turns out that in job shop operations and in those sorts of things, that often the mix of products was just not quite on the right scale. And so a lot of people say, well, wait a minute, if there's robotics 1.0 and robotics 2.0, right? Well, what was the precursor? And I think this is important. This slide here is really what robotics 0.1 was. It's the world of science fiction, because this robotics have actually, the idea of a robot, we humans have been discussing since the days of Aristotle, right, in times BC, right, where we've been always fascinated with the idea of creating automatons, replicants of ourselves. It's kind of ingrained in our psyche. And so, unfortunately, this has skewed most lay people's vision of what robots really can do. When we see things like C-3PO and Rosie the robot, even though it's a cartoon, right? And the reality is, right, robots aren't nearly that capable as humans. But an interesting thing that I like to point out about all of these examples from science fiction is, in fact, they're all helper robots. All these visions from our science fiction precursor to real robots, interestingly focused not on this idea of the lights out factory, but on the idea of symbiotic robots. Nonetheless, popular application areas that robots are popping up, whether they're robots 2.0 or robots 1.0, co-robots or traditional, right, is many of these same areas of palletizing and depalletizing, material handling, machine tending, and of course, quality inspection and assembly. We're seeing a lot more. And these are kind of where the classic hot button applications are, at least the bulk of things, but they're going into many different areas as well. And when we're integrating a co-robot, a traditional rule of thumb has always been that the cost of integrating a robot into a manufacturing process generally costs 4 to 10 times the cost of the robot. The reason being, you have to do a risk assessment, you have to pay for those safeties and guards. There's a lot of feeding of parts and fixtures to register the parts, part presentation. The grippers, of course, themselves and part handling. and like conveyors and such. And of course, a big effort is the software programming and integration to integrate it with the surrounding systems. So when you're talking a cost of the robot on the order of $40,000 to $140,000, then yeah, the overall cost, you know, by this rule of thumb, is around 160 to over $1 million. But co-robots, one of the areas they're trying to reduce those costs is obviously the guards and the safety systems are built into the robot. Again, they're intrinsically safe. That's a way to save money. But the big issue is in integration and programming. We're trying to make these, again, interact with humans and traditional workers rather than bringing in the programming experts all the time. So, and I want to point out, again, we've tried to say you still have to do a risk assessment even with cobots, but they are safe within manufacturing safety guidelines, right? And of course, the big ISO standard on safety is 10218. That's been around for a long time. That deals with robots and robotic devices. It's this new standard, the ISO 15066, which is the specific ISO standard on collaborative robots. And that's how this, again, fits into the existing safety within the plant. This just allows for specific types of robots only, right? The elimination of certain types of fencing, but it's not an elimination of safety, right? It's an exchange of maintaining safe systems. I'm not going to go into the details of what the standard is, but just keep in mind that it is within the recognized ISO standards for safety. So again, as we talk more about the cost modeling, as I hand this off to our next presenter, you know, I want to keep in mind these key considerations, right? Of whether it's, you know, robots versus cobots, 1.0 versus 2.0. Cobots still require a risk assessment. They are intrinsically safe, but you know, you have to be concerned about the overall work cell because safe robots can do dangerous things if given sharp things and that sort of thing. So there's still a risk assessment is necessary. Many of the existing cobot applications that we see out there in the factory floor, many of these are traditional 1.0 kind of applications, just without the speed and the fences of a traditional 1.0 application. And that's a key aspect, right? Cobots rely on lower speeds. And so when you're doing this, when you're trying to get into collaborative robotics, you know, it's important to think, is it really appropriate for my manufacturing task, particularly if you have an existing line with an existing takt time? You know, is it going to fit? And one of the key aspects is if it's truly collaborative, so if the human's doing something and the robot's doing something, you know, what's going to happen if the human gets distracted? And I'll say, as in kind of closing, right, a broken arm does meet the ISO definition of a recoverable impairment, right? These are still robots that are potentially dangerous. It's just that they have some built-in safeguards so that they operate in a safe way around humans, but you still need to do the risk assessment. And so with that, I'm going to turn it over to Jan Anders, who can then talk more about the details of cost modeling.
So welcome. As Richard said, I will talk about how we can look into the cost advantages of using different level of automation in a production. And what I'm presenting here is based on work we do here at the testbed. So I hope one day you will be able to come and visit. And I do this together with my colleague Ben Haley here. So what we are going to look at is how can we estimate the cost advantages of different manufacturing alternatives. And in this particular case we discussed today is low automation versus high automation. How can we get an idea about the cost? And this is based on work we do here in technical cost modeling. So what it is, by setting up different production setups that Ben will show later on. How can we look at part cost versus volume? What is the cost segmentation? What is energy cost, tool cost, labor cost, investment cost? And what is the potential, or what is the return of investment? Of course, when we go in and invest in robots, we have a capital cost coming with. And what is the cost sensitive to? This is more or less what our cost modeling tool provides. So just to give you an idea what we mean by technical cost modeling, I'm sure most of you are familiar with what we say ABC costing, activity-based costing, where you have information from history of your production, and by that you predict how will the new setup be. In the case when you go into new technology, new materials or new equipment, then you don't have enough information on history. You have to take into account what is information I also have from scientific information from that process or that material. And technical cost modeling help us to have a better understanding of the predictive cost we have on our product. And this is, of course, valuable when we have new techniques we want to implement or new equipment we want to implement in the manufacturing. This said, when we talk about cost here, we have just to make it sure. If you look the cost of the product when it's sold, of course it has everything including tax and profit and everything. We are fixing on the manufacturing cost, what is variable and fixed cost. So that's equipment, installation and purchase, of course, of the equipment if needed, maintenance, plant operation, tooling, material costs, labor costs, consumable, and utility cost. That's the cost parameter we are referring to. So in the next example here, we will this is just a made up example so you understand how this technical cost modeling work. And by this, I leave the word to you, Ben, and I will start this here and you take over.
Okay, can everybody hear me, I hope? Good. All right, so we've developed this software tool in Mac and MD Lab that allows us to lay out a manufacturing line in software. You can go ahead and start. And this is a simple demonstration of the capabilities. So we have in this example just a simple machine, a generic abstract machine that takes in some material and produces widgets that need to be transported to a warehouse. So we have different methods of operating the machine. We'll start with the human operating the machine. And we also have some choices about how to transport the finished goods from the machine to the warehouse. So we'll start with the human doing that transport job as well. So once we've laid out all the steps in our simple process here, we can connect them up. And once everything is connected, we can look at the overall costs and start to do some simple analysis on which cost segments are driving the cost at each stage of this. So we connect up all the different elements in this simple manufacturing setup here. And then we can start to do some analysis of the cost. We have a couple plots at the bottom that are showing, first of all, the cost per unit manufactured. So the x-axis is the production rate, varying from 10,000 parts a year to 50,000 parts a year. The y-axis is the cost per part. So we're varying from over $8 per part down to less than $3 per part. The other plot shows how those costs are broken down into different segments. So we can track how much of each part is going to capital, labor, training, electrical power, and the material costs being used. Again, this is a simple example with just a few categories. We're demonstrating what we can do with this tool. We have a few parameters that we can vary for each one of these steps here. If we change the hourly wage of the human operator, we can see live in the plots the impact on the cost and the cost segments, how the costs are broken down. Similarly, if we change the wage of the human who's doing the transport, or with the machine, has a fixed cost maybe of $250,000. If we amortize that over 12 years rather than a 10-year lifetime, we can see, again, how the costs change. So these are the kinds of calculations we can do with this. So in a robotics 1.0 approach that Professor Voiles mentioned, we can start to modify this line. We can say, let's take the human transport out and replace it with an automated vehicle, a robot transport. So this robot then would take the finished products out of the machine and transport it to the warehouse. So we can, just in the software, we can change this up and see what the effects will be on our costs. So once we have that line reconfigured, we can go and update our plots, and we can see the change in the unit cost from over $8 per part to less than $7 per part at low production rates. And we can also see the change in the cost segments. The cost now is not quite so dominated by labor. There's more capital expense. If we continue with this robotics 1.0 approach, we can also take the human operator out of this line and replace it with a robot operator and ask what effect will that have on our costs. So we connect the robot in. Now we have a fully automated line with no humans. We can check and see what the effects on our cost are, and that brings our costs down even more. The cost per unit, and when we look at the cost segments, now we'll see that there's no more labor cost. We're dominated by capital costs and power and material costs. Another thing we can do with this software is ask questions like, what if we add a second robot operator? If we think maybe that's a bottleneck that is limiting our costs, we could add another robot operator to drive the machine. And what effect would that have on our costs? We'll see in this example that's actually not a good move. It increases our cost per part, and that's largely due, when we look at the cost segments, to the increased capital expense. So we know just by playing with the different configurations in this software, we can explore different options with this simple manufacturing line. Another thing that we can do is break out the specific costs and identify the cost drivers for each of these steps that are changing. So at low automation, we see the costs are driven by high labor costs. And when we go to high automation, the main cost drivers are capital and electrical power, both for low production volume and also for high production volume. If we go to the next, there you go, you see the same effect for high production volume. Labor costs are dominant at low automation, and capital and power dominate at high automation. Again, this is a made-up example to demonstrate what we can do with this tool. In the next example, you'll see a bit more involved calculation with many more parameters for something that we're actually doing here in the test bed at INMAC. So with that, I'll hand control back to Jan Anders.
Okay, so what you saw here is the principle how the cost modeling tool works. It's a drag and drop, easy to be used to get an estimation of what is the advantage I will have on a change I have in my production. One thing should be said here, it's always very dependent on if the robot is dedicated just to this process or it's utilization based. That means it can be used at other operation. And one of the advantage with a collaborative robot is easier to move for different operation. Now, sometimes we can go from more high cost dedicated line to a utilization based robot, and that will take down the cost. There is an advantage. The next example here is a process that we have here at the test bed. And this is a new way of making composite part, continuous fiber, carbon fiber parts we primarily work with automotive here, example with Volvo, Hyundai, and Ford in these examples here. So what the process is that you start with your composite raw material, you make a skeleton that is all the load bearing capability. You do a second operation where you cover it, overmold it, and you have your final part. This is a simple link arm, but we have worked also with larger example like car doors and so on. Let me show you a video here so you have an understanding of this process. And of course, you're more than welcome here when we can travel around to come and see it. So here you have the setup, the raw material. This is an oven. Here is a 3-axis table and a 3-axis movement of the head. So so it's 6 axes together. So we can create any shape that we want from this load-bearing skeleton. It's kind of a 3D printing, but as you say, the cycle time here lays between 1 and 2 minutes to make, also for making a car door. Here is the raw material. You can follow the red dot here to the left. Here is the preheating, and here is the fixture for the layup of this skeleton. In this case, a very simple. You see it laying around some bushings. That is going to be the load introduction point in the application. Then it's handled. So the first one, this one to the left, is kind of a robot as well, but this is then the manipulation robot that handle the skeleton, and it's taking it into the, in this case, an injection molding machine. We say this looks very slow for the reason it's done here with all safety precaution to not destroy anything of the equipment. Here it takes the finished part and it loads the new skeleton for the subsequent molding. It takes it out, and then there comes another robot that do the scanning, and that is for dimensional control. So we have a full scanning of the product done with a hexagon Leica system. So here you see the two element, first skeleton and then the finished part. So now you have an understanding of the process, and of course you saw there is at least 2 robots involved. So let's look now in 2 cases. We should say this is based on 300,000 parts per year, 3 shifts, 8 hours each, and 240 days per year. And here in this case, this is the setup, and around the ring here you can see the 2 robots. And in the low automation, these 2 robots are replaced by a person operating this transfer and the quality check. Here you can see the investment on the left for this setup. It's about 1 million. And here it is about 150 less, and that more or less reflects the cost of the 2 robots that are taken out. And as mentioned, in this case, we are looking at manufacturing costs, but now we take in all the costs that we have associated with this. And all those cost drivers, of course, is equipment, is all the consumable, indirect, direct labor, compressed air, sewage, water, energy, plant operation, tool costs, and material. It covers all the cost drivers that are related to this process. And in the high automation case, here you can follow the different steps, the preforming, the transfer, the overmolding, all the steps you saw. You can see the cost go from the first step, 123, and the final cost, when it's gone through all the steps, is $197. And here you can see what is labor, material, equipment, operating cost. And the cycle time in this case was 2 minutes. Slightly over 2 minutes. Now we add the low automation case. So now you can see the low automation case to the right here, and you can see how now labor comes in and are affecting nearly all the steps. The first step get lower, for of course the capital cost went down there. So, and here is we have went from $2 to $3 per part, and the cycle time went up from 2 minutes to slightly over 2.5 minutes. So now we have got an idea of what this and change in automation will cause us. So now if we go back to the test bed here at IMI, the equipment here in the middle, it's the equipment that you have seen on the video. Now we put sensors as many places as we possibly can and have an interacting with the sensors of the production line. And now we talk sensors in the equipment. We can also have sensors in the application. And this information is then coordinated and showing up on these screens that is on the wall in the manufacturing floor. So here you can see the 2 cases, and you can follow the cost evolution. If you do a change, what will happen to the final cost or the different cost segmentations. So this is a way to move the information down to the production floor, so more people can be part of influencing the cost of the product. This work that have been going on here the last 4 years, we have also then looked at if we have a low automation case, still for the same part, where we produce it in the United States. Lowest expensive and most least expensive and most expensive. And if we go to a high automation case, how it might change. And this is related to energy costs and labor costs in different states. But also we looked on a global scale with help of data we had from a federal system here. And there is one thing you can see, you should not produce in Norway. It's the least favorable if you have a low automation case. And if you're going to move a low automation production from Asia to America, the price will more than double on this part. Now, if we go to a high automation case and look, if we're going to move it, it's about 50% cost increase of the part. And then you can say if in Asia they want to go to a high automation case, they gain maybe 8%, while we here will gain over 60% going to high automation. So you can see the competitiveness by automation if you compare on a global scale. So as what we have shown you here now is what we have here in this part of the test bed. Here we make the raw material. Here is the rest of the activity, subtractive manufacturing and also assembling. But it's all now being connected up, so we have all information flow going between the two sides. And this intelligent manufacturing test bed that we have here, it's really to be a platform for you, industry and university, to work in, help to accelerate digital transformation. Maybe before you start to involve too much of your own company and too much disruption of production, this could be a place where you can test and also get help with the test cost estimation of it. And it's also to prepare students, teaching, and also workforce development, have courses here at the testbed. And of course, being a network place where we hope we can help to accelerate this kind of steps in the Indiana industry. I think by that, I now leave over to Dave that will talk about this Industry 4.0 robot alternatives and how that can impact in different examples that he will show.
Okay, thanks everybody. So as we mentioned, we're using collaborative robots or co-robots. You can get all the same advantages that you just saw with automation, but they're even more dramatic in this case, since the co-robots themselves are cheaper, they're more flexible and safer, so you can deploy them more places without a lot of changes to your current workflows or shop layouts. So what you see on this screen here is a sampling of different commercial collaborative robots or co-robots that are on the market today. I'll refer you to this Cobots Guide website where you can see quantitative comparisons between these different platforms. So certain things you need to consider when you're trying to figure out if you should buy one of these and which ones to buy. So first characteristic you want to consider is the payload. So what's the total weight your robot will need to carry? Most of these robots' payloads do not include the gripper. So you get to factor in how much the weight the gripper might have, plus about 20% more for your part variability. Next characteristic will be the reach. So what is the farthest distance your robot will need to reach once it's mounted, including the drop-off location? And depending on how complicated your workspace is, would dictate how many degrees of freedom or number of axes your robot is. So for more complicated types of interactions or workspaces, you'll need an increased number of axes. And then repeatability. So what is the repeatability needed for your task? How precise do you need your robot to be? when repeating these tasks. Speed, again, as well. How fast do you need the robot to move? What is your tack time you're trying to get? That's also another distinguishing characteristic. And then weight and mobility kind of go hand in hand. Is your robot going to be mounted, or are you going to move it in a physically fixed mounted position, or are you going to move it around your factory? So then you want to consider how much weight the robot has and how easy it is to move around. There are also some platforms with single and dual arms. So do you need a single arm robot or a dual arm robot? And of course, price, right? How much is it going to cost and what's your budget? And so to summarize kind of the reasons why you would choose a collaborative robot versus an industrial robot are the following. It's a fast setup time, it's easy to program, it's collaborative, and it's safe to work with. It can be deployed flexibly in different places in the factory floor, and has fast payback. And so on this next slide, there's a video which is produced by Universal Robotics from their perspective, but it is representative of the typical commercial collaborative robots in general, which talks about these different advantages.
Once it actually hit the floor, we got it unboxed and we found a stand for it. And I think within 45 minutes, we had it up, powered, and we're actually programming the robot, just doing simple back and forths and pick and place.
It was really easy to use. I would say it took a third to half of the implementation time out of it based on the previous experiences I've had.
The process of the robots were actually a lot simpler than I had expected them to be. If you can work a smartphone, you can pretty much work these robots.
Programming the universal robot is very straightforward. Anyone with any sort of ability to think logically and can envision how a process ought to run could program the robot. The screens are laid out friendly. The commands are almost self-intuitive. It comes with a manual that you can consult if you need to, but you don't need much of that.
When you push the button on the teach pendant, you can grab the end of arm and move it to whatever position you want, and then once you release it, it can set the position and teach it as a point. It made it a lot faster and easier to program that way.
Honestly, if you can write a to-do list, you can program a robot. It's just simple down, just from top down logic, and it's fairly simple to do. The most beneficial part of the robot is actually the interface controls. So you're actually right there with the robot and you're troubleshooting as you go. So it takes out a lot of time other than me having to come inside the office, run simulations of my programs, take it back out, boot it up, see real time what it's going to look like. You can actually do that from the handle.
So the collaborative robot allowed us to have the robot and a human working in the same workspace. They're working in a pendulum type of an operation where they safely can interact. It's a very hand-in-hand kind of an operation between the two.
We've got two robots working with humans. The first robot's actually cutting wires off of the motor field. That's a potential carpal tunnel syndrome application. I mean, you're cutting about 16,000 wires a day by hand. And so we thought that was a great place to put a robot, let them potentially get carpal tunnel.
The fact that the robot is a cobot, a collaborative robot, it's important because I have no space in front of my production line. So I have only 6 foot of space left. And it's not possible to install a regular safeguarding. So that's why I choose the universal robot on this application.
With the universal robot arm now is more, I would say, at least 100% safer. Before, you had to put your hands close to the brake press, and there's a good chance that once in a while the brake presses, some of them do have defaults. Something could, an accident could happen at any time. So with the universal robot, there's no chance of anyone getting injured.
In our history of automation here, we've used conventional industrial robots and we had to build a large enclosure, separate the people from the robot, which takes a lot of space. It's extra cost. It's less flexibility. It is a safety concern. If someone defeats the interlocks on a robot enclosure, we don't have to worry about that with the force sensing in the universal robot.
I asked our partners, Bros, to show me how the safety system works, and we wrote up a program that allowed me to walk in its way as it swung back and forth. I was pleasantly surprised. It didn't hurt, and it sensed me immediately and stopped, just like I'd want it to.
The robot's very sensitive to outside force, so we really like that, because it's one thing, again, to say that the robot can be used without guarding, but it's another to use it safely without guarding.
So we came up with the idea to do some sort of mobile force, but the challenge is, how do you do that with all the safety enclosures? I came across this idea of a collaborative robot, something that could work with humans, that you didn't have to be afraid of being around. When our workers come in the morning, their task is no longer to go do some monotonous task. It's to go take their robot and deploy it to whatever job it needs to do that day. And that robot's going to move all around our sheet metal department while it does that.
When we do set up that first job, we'll do countersunk holes that will end up capping. So if it moves to another job and then comes back, it's simply just taking the caps out, remounting the robot arm itself. Usually it's going to take us about 30 minutes to get it back in the ground and powered up. And then after that, it's just as simple as loading the previous project.
We're able to quickly redeploy these robots to completely new tasks in very short order. We have all of the bases that we can transport around on wheels and slide them from press to press and application to application. That's been hugely beneficial to us.
So the last advantage is payback. And so the ROI, return on investment of this, ranges based on the particular application and configuration of the robot, but typically it ranges anywhere from 2 to 6 months. So there's another type of collaborative robot on the market today, and these are called autonomous mobile robots, or AMRs. And so this first set of AMRs are used as autonomous mobile robot bases with various payload holding capacities, and they focus on material handling. Most can be outfitted with additional accessories for transporting or pulling items along the factory floor. This next group focus on order fulfillment and logistics operations. They're designed to work with human workers, bring items to them, instruct them what items to pick, and transport different items to the shipping areas. The Fetch platforms also have a mobile base robots, along with specialized robots for moving entire shelf units, reading barcodes for inventory management, and conveyor belts to help process work in progress on the floor and move from one machine to the next. This next set here of AMRs are looking to automate forklift operations safely in the presence of humans. Again, they also have different size capacity vehicles for different applications, and they're useful for moving pallets around the factory autonomously. And finally, in this last group here are what we call mobile manipulation platforms, and they combine a robotic manipulator like we saw before with a mobile robot base. And they're designed for autonomous picking and kitting of orders, and just to basically be a mobile collaborative worker on the factory floor. And so in this next video is a case study which shows one particular type of AMR, specifically the Locus Robotics platform, and see how it's been used for order fulfillment for this one particular company.
Marley Lily is an online company that is solely based on personalization items. Every item is personalized and shipped out to very happy customers.
Because 75% of the items that flow through our facility are customized, it makes it challenging to collect those items to ship the customer one package instead of multiple packages.
I was a little skeptical. I've never worked around robots, dealt with robots at all.
The deployment process was actually quite simple. Our IT team worked with the Locus team to develop the solution on the back end. And I was actually quite surprised because when we went live, it was fairly seamless.
The most surprising thing was honestly how they pretty much do everything for us. It was super easy for everybody to adjust to the new process.
It truly is impressive the way that they can guide themselves and direct themselves around the facility without running into anything else. They really do have a mind of their own, but it's a controlled mind.
We are much more efficient with Locust robots. We ship 3 times as many orders as we used to.
Basically, our entire fulfillment process was changed when we migrated to Locust. The dashboard is a great tool that we use to monitor how many picks per hour we are getting out of our employees. And now we can go in and review an employee's productivity at a moment's notice and make corrections very quickly.
Peak at Marley Lily, if I could describe it in one word, is fast. Everything is so busy. It's 24 hours. It's nonstop. You have to get orders out the door, and Locust Robots helped us with that a lot this year.
Right now we have 15 robots working here. During our peak season, we upped that number to 25.
It made everything a lot faster, a lot less looking around for missing items. It was I'd say the most efficient Christmas we've had during peak season.
I think the big thing is how surprisingly simple it is to work with the robots. And it's not that we're eliminating human jobs, we're really just increasing the efficiency and optimizing our pick operation.
We have grown so much in the past 7-8 years, and so we've implemented a lot of new processes. Locust was one of the largest processes we implemented and the smoothest.
We want to try to stay ahead of the curve, ahead of all of our competitors, and in order to do that, we need to stay technologically advanced. And I think Locust is one avenue that will definitely help us to reach the goals.
Okay. I'm just gonna switch out from this for a second. Okay. So we have a number of different co-robots here at INMAC and the test bed. Specifically, we have this fetch and freight robot from Fetch Robotics. So the fetch is a mobile manipulator platform, and the freight is autonomous AMR. These robots can work individually or together to carry out a variety of tasks. In this video, you can see the fetch robot autonomously navigate to a CMM machine where it uses its onboard perception system to identify and locate a part for pickup. And so once it identifies where it is, it's going to plan its motions for the manipulator and the end effector to grasp the part, then transport it and drop it off at a designated location. So it's doing all this using its onboard intelligence. On the right, you can see an image of the Omnivair AMR that we have in the test bed. These are mobile bases, and in this configuration, they've been outfitted with a robotic manipulator and a tow rack for picking and material handling tasks. And eventually, they'll be able to emulate any type of material handling conveyance that you could think of in the factory. So in the future, we're going to be hosting some workshops where users will get to learn how to use and program these different cobots for various Industry 4.0 tasks. So again, please stay tuned for when those will be available. We're allowed to do those after the COVID situation has wrapped up. Okay, so just to conclude, want to reiterate, we have a pretty neat, unique intelligent manufacturing test bed here at INMAC, which can be used to showcase and demonstrate different Industry 4.0 capabilities. We touched on the technical cost modeling and collaborative robotics components of the test bed in this workshop, and other workshops have touched on other aspects of it. In addition, what we've shown here for the co-robot applications, we're also working on integrating machine learning and big data and studying the mechanics of motion for robots to enable autonomous intelligent behaviors to improve their robustness, allow them to adapt to various situations. So again, just please think of the test bed as a platform for industry and university to develop and validate technologies, accelerate some of your digital transformations, help prepare students and workforce, and also as a networking environment. And so now I'd like to switch over to discussion, where we can start open up for discussion and Q&A using the Q&A tool in Zoom.
Thank you, David, and thank you, Richard and Jan Anders as well for the presentations today. Again, participants, thank you all for joining us today. We do have, we look forward to some questions, and I'll offer just a couple questions to get the discussion started today, and we'll continue to monitor this Q&A board for a few more moments. First question for the panel is, how might a company work with Purdue to develop the robotic applications for their company, including any interests in mechanics of motion?
I don't know who's going to answer this. Of course, we have the test bed here that is then joint facilities between many faculties, but also in MAC and WIN. And I think you should always see it as part of your assets out in the industry. We are here for you, and I think we are very motivated to find ways to collaborate. And then the funding for this, there is different funding mechanisms, both through in the state of Indiana, but also via WIN and Purdue. So I think depending on your task, you should contact us and see what we can, how we can help. And we also like to be some kind of a gateway via Purdue manufacturing initiatives and WIN, how we can help you connect with the right faculties. Sometimes joining a university, where do I go? Who do I talk to? We would like to be some kind of connection point. And here I will also point to Mr. Ted Fiok, that you might know, that is helping and distributing you to, or connecting you with the right people in the system.
Thank you, Professor. We do have a couple of questions for the panel from our industry participants. The first question is, do we have any current project or quality checks for surface defects done by robots?
I don't think we have any, let me see, I'm not sure if we have any current quality checks with co-robots applications currently. We do have some coordinate measuring machines. We have some mobile surface and gross measurement capabilities, and of course some co-robots. So we just haven't, again, a lot of things have been delayed due to COVID of actually getting applications up and running, but that's certainly an opportunity we're equipped to do and would like to talk about.
And in addition, thank you, Professor. And in addition to that, we do also have, as regards to dimensional checks on a more traditional robot, there is a hexagon Leica scanner, and that was featured in Professor Munson's video outside of the injection molding machine. So it's a high resolution laser scan that provides a very timely check right at the machine, again through a Leica scanner through one of our partners. So that is a demonstration that we have, but we're certainly interested in developing new tools, new demonstrations as well. Okay. Another question that has come in from our participants for the panel is, it's a question of how much product definition needs to be determined for a company to use the automation capabilities of the test bed. So I think in addressing that, it really does depend on the project. I'll just start the answer in this case. It really does depend on the project, the more information, the better. But even if it's to help scope, an opportunity or to scope a demonstration or a capability through our staff, through our faculty experts, and others that are engaged in Purdue's testbed facility, we can work with companies to develop product definitions.
Yeah, I would agree with that, and also say, like, as long as we know what the tolerances are, we can design the appropriate fixtures and procedures to accommodate that.
Correct.
I
Okay.
should say something when we come to the measurement and quality control. Many times you have expensive equipment in a room somewhere that you go and you do the measurement. What we have seen capability here is to have that the measuring arm that you saw on a robot mounted on one of the cobots or one of the AGVs. So now we come out and we can do measurement at that machine. We don't have to move the product into a special room. And that measurement opportunity can go from a different machine, not dedicated to just one. So this is like a rotating quality control man walking around in the production. And that, of course, is an enormous cost save to have it automated.
Thank you, Professor. And I have one more question. And this is for you, Professor Munson. How would companies participate with Purdue to apply the predictive test cost modeling application? What would be the first steps?
Okay, I started and then I will leave to Ben to continue that. So the cost modeling have been developed over many years, and the fine-tuning of that is by interacting very closely with company. And I should say, so we mix our predictive capability with the reality of what the industry is interested of and what information they have access to. And to work with us, today we are doing it via the testbed here, but we are very close to do the next step of that. And I leave that to you, Ben, to say the next step we're going to take with this cost modeling tool.
Yeah, so we're working on a web application for technical cost modeling. The demonstration that you saw today is the standard desktop tool that we've been developing over the last couple of years. And that's perfectly capable, but it's hard to install and get configured on anyone else's computers. So we're developing a web application that we'd like to explore and develop the capabilities of, basically. So if you're interested in that, you contact me. My email is up there. Contact Dr. Monson or Mike Ursum, who you see here. We'd love to talk to you about how we can partner with you to develop this capability. That's something that's an ongoing research project for us.
Great. Well, thank you, Ben. And again, thank you all panelists for your preparations for this webinar. And most of all, thank you to our industry participants for joining us today. Please stay tuned for additional events from in the form of webinars, and as soon as we're able to, in-person workshops where we can come in, work with our experts, work with some of these technologies, and we can talk about how potentially we can collaborate directly with industry. So we have a wonderful capability here in West Lafayette. Again, thank you all who participated with us today, and we look forward to engaging you in the future. With that, I will conclude today's session. There will be a survey that follows, and a recording will also, some information about the recording of today's session will also follow. Thank you all very much. Have a great day.
It looks like beer jelly.